Hi, I'm Professor Usaki. Before we start the lecture, there are a few things that I need your help. First, please mute your microphone most of the time unless you are asked to provide your feedbacks or questions. Second, if possible, please use a headphone or earphone instead of a speaker to receive the best voice quality of the lecture. In addition, using a headphone also helps us to avoid the echoes when you are expressing your thoughts. Finally, this is an interactive class. You may be asked to answer a few pop-up questions during the lecture. Please pay attention to what's going on right now. Thanks for your cooperation. Now, please sit back, relax, and enjoy the lecture. Glad to see you again in EECS120A. So today we are going to continue our discussion on how to optimize our design. And the technique that we are going to talk about is not really complicated. It's just a simple tool called Karnaugh map that try to help us simplify a given Boolean expression. But before we start, I guess this is the lunchtime, and you are probably eating your lunchbox, or you have finished your lunch and you feel kind of like drowsy in front of such a desk. Well, so this is actually the desk that the desktop I have. So there were one day that my PhD students were asking me like, oh, professor, what your desktop looks like this, and this is actually my desktop. Well, forget about those, anime characters on the desktop. So one thing I found interesting is that, well, this is actually the desktop that this is what I actually took a photo for the last lecture during a pop-up quiz question. And you guys must know that we always have some kind of counter timer on top of the screen. And one thing interesting that I found is that, this one is actually my original the computer that I'm using, and you can see the timer is 44 seconds, and on the Zoom is actually 48. So it shows that whatever I said, you guys are going to hear it 4 seconds later. And I know we are still having quite a few of you having issues getting into Zoom. I don't know how to solve this because every of your information looks about right, and as long as you are logging using a UCR account. So one thing that I would encourage you guys to try if you are if you're on YouTube and you are unable to log in, is that you can probably log out all the Gmail accounts that you have and try to relaunch your Zoom again, and make sure that this time you click the UCR account to make sure it's working. Right? Because the reason why I want to do that, if you don't want to participate in a class in terms of asking questions online, but as you can see from my screen, I did watch you guys over the YouTube through the chat screen that you can see here, and knowing that you guys are here, and if you guys are asking questions, what kind of answers you gave, but it's already like 30 seconds delay comparing with my original computer. So sometimes if I saw something, I may not be able to respond to you immediately. So that's one thing interesting that you guys should know. And from this this shot, you probably know how busy I am when I'm doing a lecture, because I'm not only monitoring the Zoom, I'm not only broadcasting my lecture, watching my slide, look over your survey polls, but also try to interact with as many of you as possible, right? So now I feel maybe the right thing for me to do is still be a professor, and hopefully we can back into classroom to teach next academia year, so that I don't have to survive as a YouTuber, which I think is terribly lazy when I am doing the lecture. All right, so before we start, as our tradition, we always want to bring something back into your mind. So here is the recap. So last week we talked about, from truth table, you can write any truth table in the form of Boolean expression, and Boolean expression is a lot easier. And however, the direct conversion from the sum of product terms into sum of product terms, they are not the most concise. They are not the most simplified format. So to simplify your Boolean expression, there are a few ways that we can do. For example, the fundamental approach is that you apply the laws in this table, like associative laws, distributive laws, identity laws, commutative laws, whatever laws, De Morgan's law, consensus theory, uniting theory. And if you and you can exhaustively search all these laws to see if your Boolean expression is optimized or not. However, it's such a exhaustive process that would discourage anyone doing digital design, right? So and for example, like this question we talked about in the last week, right? Using uniting theory, theorem, you can potentially get these three terms. However, this is not a minimized one, because if you use the what's the name? What's the name of it? Yeah, it was one of the laws, which I don't even remember its name. You can make it as simple as this one, right? But this is still not the simplest, because if you use distributive laws, it turns out give you this one, right? So this approach is not really what we wanted. So another and most of the time, like, okay, sometimes when a professor shows the answer, you guys must have this. Well, I'm sure that you are going to add a few words before the sentence, right? Like starting with a what and then something something, right? And like what the something, how can I know this, right? So this is too complicated. So that's why we talk about this tool called Karnaugh maps. It's an alternative to truth tables to help visualize adjacencies, because uniting theory, uh, um, um, because the adjacency, because the uniting theorem is based on the terms with shared literals, right? So the steps of doing this is that let's create a 2D truth table with input variables on each dimension, and adjacent columns and rows only change one bit in a variable, and fill each ij with the corresponding result in the truth table, and identify the onset means that a size of in power up to like 1, 2, 4, 8, and unite these terms together, and finding the common literals in the main terms, and find out the minimum cover that covers all the ones in a graph. So, and then sum with this united product terms of all minimum cover onsets. So that's the whole concept of Karnaugh map. So, but how to do it, right? So last week we tried a two variable case. Like for this truth table, you can convert it from the left hand side to the right hand side, and then we are looking for onset with size 1, 2, 4. Because this is a table with 4 entries, and definitely there is no 4, but there are 2 2s that is sufficient enough to cover all the 3 ones we have in the table. And for this one, you can obviously tell. Well, you can tell there's the common thing here is the A prime, and for the other one, you can tell the common thing is the B prime, right? So that's how the Karnaugh map will work. And then if you sum them together, is A prime plus B prime. So But most of the time, you're not so lucky that you only have 2 variables. So what if I have 3 variables? It's still the same, right? You just need to make sure that you find a good map that try to map your truth table into a 2D dimensional, a 2-dimensional representation. And it turns out that in one of the rows that one of the dimension that represent 2 variables, you have to use gray coding instead of the regular coding. You would think that jumps from 0 to 4, 0 to 3, like 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1. But instead, what you should use is 0, 0, 0, 1, 1, 1, 1, 0, because in this way, when you are using in this way, when you are using the one when do it again. Okay, so in this way, when you are jumping from 0, 1 to the next one, you are only changing 1 bit. So that's you are only changing 1 bit, right, instead of changing 2. So that's why you have to use gray coding. And remember, the basic idea of K-map is that you can only change one in your adjacent columns or rows. So in this way, if you fill the table correspondingly, then this is the 2D representation. And if you try to connect all the onset together with size of 4, then you can easily get A prime plus C prime and as the evaluation. And if you find this familiar, it's exactly the same truth table that we have seen in the very beginning of the problem, right? So in this way, you can see how easy is it to make how to simplify your circuit design with K-map. And you can definitely combine K-map with some theorem, which I kind of like discourage, because why do we? So if you have a one-stop solution, why do you saying that, okay, saying that your hometown is in the Bay Area, right? And if you can directly fly to Santa Clara, well, San Jose, right? Why do you have a flight going to Sacramento and you drive from Sacramento to San Jose, right? That doesn't make sense, and it doesn't save you money, right? And you still achieve the same effect. So try to get yourself as familiar as the operation of K-map as possible, so that you can use this one powerful tool to simplify all the circuit design problems that you are going to interact with the class as well as the rest of your life. So one important thing is that you have to draw a correct K-map. So right now I'm showing you 4 different K-maps. Can you guys tell me how many of the following are valid? Last 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see. What do you guys think? So right now, let me share this result with you. So 57% of you think it's C. So can I have some volunteer to tell me, to justify your answer? Can I have some volunteer? Raise your hand. Raise your hand. Okay, I have Chi Chi. Hello, what do you think?
Actually, I choose D, but
you chose D. Okay,
yes,
but I like that.
But I'm not sure about number 4.
Okay,
I
so
think
but why? Okay, so except for number 4, let's talk about number 4 later, right?
okay.
So why do you think the other two you think they are correct? So
Uh,
what are the other two?
I know the 1 and 2 are correct.
Why?
Because 1 is following the number schema of the gray code.
Okay, it's a gray coding, right?
Yes.
Okay.
And for number 2, I just flip 1 bit.
Mm-hmm.
So
number 2 is actually you move the first row to the last row, right?
Yes.
So and what's the rule of gray coding?
So we can only like flip 1 bit.
You can only flip 1 bit, right? So
yes.
From 0, 1 to 1, 1, you flip this bit, right?
Yes.
From 1, 1 to 1, 0, you flip this bit, right? And if you go from 1, 0 to 0, 0, you flip this bit, right?
Yes.
So it's a gray coding. And why? And how about 3?
Number 3, because you are actually like moving 2 bit.
Where?
Because the you are moving the 0, 1 with the so it seems like you're moving the 0, 1 and the 1, 0.
So here's the thing, right? So 1, 0, I change this. And I have to change this as well. So I change 2, right?
Yes.
Okay, so how about the 4th one now?
Because the 4th one, I choose this to be correct because I think it only changed the 1, 0 and 1, 1. So I consider that flip 1 bit, but I'm not sure.
But if you look at this one, right? 0, 1, 1, 0, right? You are changing 2, right? It's exactly the same case as the 3rd.
Oh, okay.
Right? So if you don't think this is valid, why do you think this is valid? It's not.
Yeah.
All right. Okay, you got it. So right now, I think we got a consensus that if you look at this one, right, then if you look at this, then how come my iPad is not? Okay, the first case, the second case, everybody agree is right, but the 3rd and the 4th case is not correct, right? So 2 of them are valid. So you can definitely rearrange your rows in a certain way that help you to get more a larger onset. However, you can only change it in a way that's not disobeying the law of gray coding, right? So that's why only 2 of them are correct, right? So given you know how to draw the Karnaugh map, right? So for this 4 adder, you will find out no matter how I rearrange this columns, rows, I can never make this 4 ones connected together. So unfortunately for this 1 bit 4 adder, you still need 4 different terms. Okay, so today, well, since we talk about Karnaugh maps, they are very important. They are very important tools for us to simplify our design. So we are going to give you more example practices on Karnaugh maps. Are you excited? Maybe not. And if we go through these examples quickly, then we can potentially look at some design examples that may help you in the rest of the quarter. Okay, so the first question is still about the editor, and last week we talked about the outcome. But how about the carry from the for editor? Okay, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so according to the result that I got here, 50% of you think is C. The second most popular answer is D, 29% of you. So it looks like only about half of you agree with one answer. So can I have someone to explain why you chose that answer and why do you think it's correct? Can I have someone? Okay, looks like I have nobody. So in that case, then I think it's my show time. So let's start. Let's start with so how to solve this kind of question. So first of all, again, since we are in the lecture of K-map, right? So it's very trivial that you have to start with a K-map. And the right way, well, so the very basic way of doing a K-map is that you just lay out a gray coding on one column and two on the other side, right? Uh, and by remapping your truth table into this way, like you can find a few terms like you can find there are 4 ones, and if you lay out this way, they are all centric by they're all centric by this place. And so you just need to draw this one, and this one, and you will figure out all you need is a BCN, an AB, and AC, and that will cover the whole thing, right? So that's how we got the Karnaugh map of this four adder carry, right? So for this four adder, although we need uh, four ORs for the output. However, for the carry, we only need 3. All right, since no one responded to me, so let's try this one. Okay, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so this time, well, I got 61% of you think it's D. Well, can I have someone volunteer to explain why you advocate for your answer? Can I have someone? Oh, okay, I have Chi. Okay, thanks for helping us to resolve the silence because I just realized that we don't have Fox today.
It's okay. I choose D, but first I write all the expression of all the ones and then I simplify them. But I have a question when I'm using the K map. I don't know why I get another result.
Okay, so what's your result? Can you share with us?
When I just simply using the writing.
Okay, so let me draw the one that you draw, right?
Okay.
So what do you have? So what's a gray coding you are using here? Are you using the regular one?
Yes.
Okay, so it's 0, 0, 0, 1, 1, 1, 1, 0, right? And here it's 1, right? So for 0, 0, 1, it's 0. Well, so sorry, this is 0. For 0, 0, 0,
It's 1.
Okay, let me draw it again. For for 0, 0, 0, it's 1, right? For 0, 0, 1, it's 0, right? For 0, 1, 0, we got a 1. For 0, 1, 1, we got a 1. For 1, 0, 1, 1, 0, 0, we got a 1. For 1, 0, 1, we got a 0, and the rest of them are 0, right? So this should be the one that you draw.
Yes.
Okay, so what kind of, what are the onset you got from here?
Actually, I get 3, but there's 1 intersect.
Okay, so so you mean there are 2, right, basically?
Yes.
Okay, what are the 2?
Yes, the 0, 1, 0 and 0, 1, 1.
0, 1, 0 and 0, 1, 1, right? And how about the other?
The other one is the 1, 0, 0 and 0, 0, 0.
Right, so there is one here, right? So you got 2 sets, right? So if you have this, then this is probably the table you are going to draw, right? So we got A prime B and B prime C prime.
Yes.
Okay, so that's why D is the answer. Okay, thanks for saving us from the silence. And because you save us from the silence, so now we can finally advance to a different K-map. Okay, we are still going to be in the world of K-map. This is 4 variables. Okay, so we have been talking about 3 variables. What if we have 4 variables? So again, right, so for four variables, all you need to do is to map the four variables into a 2-dimensional K-map. And both dimensions will be represent 2 variables, and adjacent points should differ by only 1 bit. Still great coding. So for example, like if you have a truth table with 4 different variables, just lay them out like this. And the same thing would happen is that if I find an onset like this one, then it turns out that the common ones, they are A prime, B prime, C prime, right? So this one is A prime, B prime, C prime. And for the corner ones, you know we can wrap them around. So if you combine these 2 ones together, it will give you B prime, C prime, D prime as the common literals within these 2 ones, all right, between these 2 ones. So this is how you get it, all right? So the same philosophy. Just make sure that you can map your truth tables to K-maps correctly and try to find the right onset that covers everything, right? So I don't think I need to walk through a 4-variable K-map again, and I know you are eager to show me by how much you understand this. So why don't we try this one? How can I help you?
I think you typo it. The answer E is like B prime C prime plus A prime C D prime.
Well, we can look over it later.
Okay.
If you are willing to explain what's going on.
Okay.
Well, I'll keep you online. Okay, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so Chen Yue, right? Is that right? Oh, sorry.
Yes.
Okay, so you think the closest one is E.
Yes.
Okay, so how come?
Because you can group like the first two lines, the fourth one is in
Okay,
group.
this one and this one, right? So
Yeah.
the common set here is going to be B
B
prime,
prime, C prime.
C prime, right? So I
And
have
the
B prime, C prime here, B prime, C prime here. I have B prime, C prime here, right?
and the
And
fourth line, the 2 1.
okay, so let me use a different color. So this one, I have 2 1s. So this is A prime, C, D.
D prime.
Ah, A prime, C, D, right? So this is not here, right?
Yeah.
Okay, so the answer, yes, you guys caught my typo. It's actually A prime. Yeah, see, I did get it right here. How come I didn't get it right here? Okay, so it's A prime, C, D prime, right? So that's the answer. And I'm glad you found my typo. And because you found my typo, so you actually save us from having more 4-variable K-math issues. Woohoo, you're the hero. All right, so right now I'm convinced that you guys understand what's going on in K-maths. So right now, let's have a real design example that you might be using in your labs in the future or something, right? Well, and sometimes I found it's really funny that to look at the chat from YouTube, like a few seconds ago, I found someone that, well, I guess the answer is what? Because I don't have a pen. But now he replied that, well, I got a pen. All right. So, hey, you guys, don't worry. I'm looking at, I'm reading your chat, although it's probably about like half minute later after something happened, but it's you guys really made my day, and I know you guys are here. Don't worry. All right, so right now let's talk about like 2-bit comparator. So what's a 2-bit comparator? So there are many times in your life, every day, right? When you have to make a choice, you have to compare. Like, okay, when I go to the grocery store, well, sorry about like having the grocery store examples all the time because you need, being like under the stay-at-home order, the only place you are legitimately to go is actually the grocery store. Okay, so I have this 10 eggs and the other 10 eggs. They have different prices, they have different sizes. So I always have to compare two different things so that I know if I can make a better decision, right? So comparison is a very important human nature behavior that you are going to do every day, the same thing that in computer systems, in circuits, any logic systems, you have to do comparison all the time. So there are definitely a larger numbers of decisions that you have to make for a more complex system, but let's start with the simple one. That's a 2-bit comparator. So here is a 2-bit, here shows a 2-bit comparator. We have two numbers, N1 and N2. And for N1, it's 2-bit. It's a high order bit is mapped to A, and the low order bit is mapped to B. And for N2, the high order bit is C, and the low order bit is D. And if two things they are equal, the EQ would give you a 1. If if N1 is less than N2, then the last len is going to raise a signal. However, if none of the two above, then it belongs to the case of greater than. So we are going to raise the signal on a greater than and keep the rest of them zeros. So based on this, you can easily derive the truth table on the right hand side, right? So this is a truth table, and as you get, let's pick one, right? So for this case, right, 0, 1, 0 means that N1 is right now 2, right? And 0, 0 means that N2 is right now 0. So since 2 greater than 0, you know the greater than should be 1. So that's basically the truth table, right? Okay, so that's a 2-bit comparator. So you know you want to design a circuit with this feature, but how, right? How? So so first of all, right, you know, well, we have 4 different variables, and you know from the adder example, for each output you need a different K map, right? So you know you need a 4-variable Karnaugh map for each of the 3 output functions. So right now we are going to design the comparator using K map we just learned with a few questions that I'm going to ask. Okay, so if right now I want to present LT, what's the minimum SO Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so from what I saw from according to your poll result, it's 68% of you think it's B. But you know, sometimes people just guess, right? And they are lucky. So can I have someone telling me why you chose your answer? Maybe you are right. Other people are wrong. Other people are wrong. Can I have someone? Okay, I have Chi Chi again. Nice to hear from you.
I chose B on when I draw the K map.
Mm-hmm.
I actually grouped them into like 4 subgroup.
Mm-hmm.
And
But why you still chose B?
because when I write out the expression of these 3 groups, I get B. That's why.
Okay, so let's look at this, right? So how do you draw your K map?
I using the gray code number.
Okay, okay, gray coding, 1110, 0001, 1110, right?
Yes.
So it's LT. So let me see, 00000. This is 0, right? And the rest of them are ones, right?
Yes.
And for 01, 01, 00, so this is 00, and the rest of them are ones,
yes.
right?
Yes.
And for 11, 1100 is
all
a 0,
zeros.
so they are all zeros. For 10, 0, 0,
1,
0, right?
Yes.
So what are the groups that you found?
I grouped 0001 and 0011 into a group.
So 001. Well, say again. 00
0001
0001 and
0011.
0011. So you think they are the same group?
Yes, and I grouped the bottom 4 into a group.
Okay, so that's a group. And
I also group 1011 and 0011 into a group. Yes.
okay, so for this part, what it is, so it's actually, so this one is actually A prime, B prime, and D, right?
Yes.
Okay, A prime, B prime, D, 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 right? So how about the blue one?
The blue one I write as A prime C.
So for the blue one, right, the all A's are all zeros, right? So, and C, okay, so A prime C, so here, A prime C. Okay, we only got here, right? So maybe I have another typo. Let's look at that. So for this one, it's what? It's actually, okay, so if you look at this one and this one, right? So the A is either, one is A prime and one is A, right? So the A cannot be the common term, right? And the B prime is the common term, right? And they are B prime CD, right? This one. So I don't have a typo. So the answer is 2. Isn't that?
Yes.
Okay, so then that's the answer, right? Okay, so I'm glad that we got it. But you know, being a teacher, sometimes you are afraid that your students are just lucky. So let's try another one. How about GT? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Okay, time is up. Okay, so I got a majority of you think, well, actually 63% think it's E. So can I have someone to share your thoughts about me? Oh, Chi, you are doing it again. I'm glad, but before I call you, isn't there any other people than she is listening to the lecture now? Okay, so I can only have you. Okay, take away.
So I draw the K-map again.
Okay, draw the K-map again. So it's something like K-map, right? This, right?
Yes.
So so here I found one term, BCD. And where else can I find a term?
And there's 4 ones on the right-hand side of this.
Okay, so this one is the 4 case that you mentioned, right?
Yes.
What else?
And then the one is the 1100 and 1110.
Okay, here we go, right? So we have another term here, right? So turns out that we have E as the right answer. All right, thanks a lot for contributing your idea. Okay, so since there is nobody else and Chi is responding to me, so I guess I have no choice to send you another question. So why don't we try this one?
Professor, isn't C and D essentially just the same thing?
Yeah, you are right. Okay. Okay, let's wrap up in 15 seconds. Five, four, three, two, one. time is up. Okay, here we go. Okay, so, well, so since I have Sahas talking about the answer, so why don't you share with us what do you think? So first of all, C and D, they are the same, but are they correct?
I put C, but then I later noticed
Yeah,
that D was also the
because
same thing.
I thought I want to make them different at some point, but for some reason, well, yeah, but for some reason, why I didn't do that, right? Because if you look at this is essentially this is essentially this, and this is this, and yeah, this is just like a rearrangement, right?
Mhm.
But I didn't change it. Okay, so okay, so but why do you think either C or D they are the right answer?
So I made the K map, the 4x4 K map, and then
Okay, 4x4 K map like
uh,
this.
yeah, and then I found that all the ones go down on like a diagonal, so 0, 0, 0,
Okay,
0.
so like this, right? So
Yeah.
that's the thing, right? And if it's a diagonal, no matter how we rearrange them, there's no way we can combine them together. So we got at least 4 terms, right? But maybe it's either C or D. They are the same, but maybe they are wrong, right? Have you ever checked that out?
Hmm.
Have you?
I mean, I presume that it would be C or D because
But maybe I have another typo, right?
right.
Okay, so how about this one?
Yeah, that's correct.
It's what?
A prime, B prime, C prime, D prime.
Okay, so it's indeed here. And how about this one?
A prime, B, C prime, D.
C prime D, right? So A prime B, C prime D. Okay, it's here. How about this one?
A, B, C, D.
Okay, how about this one?
A B prime, C, D prime.
Okay, so we know these two, they are both the right answer. Okay, I will check. I will update my slides later. Okay, thanks a lot for your contribution. Finally, we got someone else to tell us the answer, right? So you guys are the heroes. You save us from the unlimited dungeon of working on 4 variable K map and this design example. But right now, we are still going to have a different type of K map that we are going to deal with. And you will find out this kind of K map actually are pretty useful for your labs. So, you know, there if you guys remember what I have talked to you about in what I've talked about in very long is that in addition to ones and zeros, there is something called don't cares. Right? So for don't cares, right, there why Verilog support that? And indeed, in circuit design, we do have don't care sometimes because there are functions that are incompletely specified. So there are situations where we really don't care if it's 1 or 0, and it because it doesn't matter, right? So most of the time we call this situation don't care. So for example, like if I want to express a decimal number using a decimal digit using 4 bits, and you know that the 4 bits can represent 15 numbers, 15 digits. However, if your problem space only require 10 digits to be displayed, there are a few empty ones like this 1111 that doesn't occur in a regular case. So this case would be a don't care. So that's in the case that you have a don't care, what we would do is that we put X in the truth table. So for K-map with don't cares, it's kind of interesting in a way that you can either treat this don't care as 0 or 1. So for this example, if we treat the X as 0, then it turns out that I'm going to get 1, 2, 3 different terms. And you will find out that, well, in this way, I would use 3 different OR gates and 3 AND gates to implement the circuit. However, well, 2 OR gates and 3, yeah. So this is not what we really. But on the other hand, right? If I can treat the x as a 1, then it just make the case a lot simpler in a way that I only need to AND or the result once and use 2 gates, right? So there's no standard answer for what we should treat the don't cares for, just depending on which one give you more advantage in simplifying your circuit. So don't care is not a demon. Sometimes it will probably help you to simplify your design if you treat them in the right way. So how about now if I have a K-map with don't cares, and which of the following could be valid? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let me see. Wow. So this time, the result is pretty interesting. So both C and D, they are popular answers, but are they the same? No, they are not the same. So there must be something that we need to talk about, right? So can some of you tell me well, sorry, so C and D, right? So it means that it's either well, two or three, they are correct. So can I have some volunteer to help us solving this bazaar? If not, I have to pick someone. So better that we have someone. Otherwise, I will really. Okay, looks like no brave is going to break the silence for now. So let me show it, right? So this is the key map, right? So let's see. If we treat the x as 1, we got a term called CD, right? If we treat this term as 1, we got the term ACD, right? So anything with CD, AC, well, C prime D, A prime CD, that could be possible, right? And if we treat this x as 1, we got A prime BC. So A prime BC, right? That's possible too, right? So right now, let's look at, but if you try this thing with 1, right? Then where's AD? So the A prime D is actually the case where A prime D is actually the case where we have A prime D is actually the case like this, right? So yeah, if you treat this one as 1, then you should also have A prime, you could also have A prime D as a potential 1, right? Okay, so how about A prime D, BC, B prime CD, A. Well, so the thing is that if we treat this don't cares as 0, right? If we treat this don't cares as 0, right? Then this is A prime, B, C, D prime, right? And this thing has to be a standalone term, right? Like C prime, D, and B prime, right? And this thing is a single term that could be A prime, B prime, D, and this thing itself needs to be stands for another term, right? Which is A prime, B, well, A prime, C prime, D, right? So if you look at 4, right, it doesn't really have A prime, B, C, D, A prime, B, C, D. It does cover 3 of this. However, it needs to be complete if you can if you have this term, right? So this one is the only one that I don't think should be valid. Well, the only one, well, so actually, yeah, so this one is actually the only, so put the wrong place, right? So this one's the only one that shouldn't be the valid one. Okay, so 3 of them are actually possible if you treat the don't cares as 1s. Okay, so right now I think we got the idea of don't cares, and we want to look at one more example. So this one, if you spend some time on lab 3 already, you will figure out that this is a very close related example. So in lab 4, you are requested to convert the decimal number into binary digit and then represent them as a 7-segment LED. So, but the whole idea is that you have to make the decimal number something different. And the key is that you have to remap your decimal digit to something else. So if so here the simple example is that I'm going to map my binary coded decimal plus 1. So for example, if I have a number that you use binary, it says it's 9 and it actually stands for 0. If it's 0, it stands for 1, right? So the whole idea of this is still the same, right? You have a 4-bit input and you use the, yeah, so this is the wrong, this is the BCD plus 1. And you have the BCD plus 1, it will give you 4-bit output. So so that's a whole idea of binary coded decimal. And as you can see, right, because we are not using anything that is larger than 9. So everything that belongs to A to F is actually don't care. So that's the final truth table you are going to draw. And you just need, all you need to do is to, again, draw K-maps like this for each of the variable and trying to find out what definition of those don't cares would help you to minimize the number of gates that you need to implement the circuit, right? So that's all your that's all this BCD plus 1 is going to be about, and that's a very similar idea as your lab. So spend some time looking over this example and try to figure out and try to correlate it with your lab. I think it would help you a lot. All right, so okay, I have Fandel. Okay, so hello, how can I help you?
Can you explain why this is helpful?
So, okay, so in your lab, right, you are going to receive a decimal number and you want to express in 7-segment signal, right? And a 7-segment signal, it only has 7 different bits to control if a stroke on your digit should be on or off. You know what I mean?
Yes.
Right. Okay, so that's very similar to what this example is aiming at. All right, you are given a number, you convert it to a different representation.
So,
right?
so it would, so from output number, so from
Decimal input number to a 7-segment.
I still don't understand how this would.
Okay, so for 7-segment, right? So this saying that you, so this is the 7-segment.
Yes.
Right. And now, if I have an 8, how do I trigger this all things? So A is actually something like 0, 0, 0, 0.
We're having 8 outputs. We're having 8 outputs, but we're having 4 inputs, right?
Well, go look at your.
Or 7.
No, you are saving 7 outputs.
7
right?
outputs, 4
but
inputs.
4-bit input.
Okay.
Right.
Oh,
well,
okay. I see,
go back and look at your Lab 3 lecture.
I see.
Okay.
Yeah.
All right.
Thank you.
Okay. So thanks for asking this question. Okay. So this is the so I would encourage you to watch the Lab 3 lecture. It's already online. And before we talk about other stuff, right? There are some more interesting things, right? So a lot of cases you are going to have 5 variables. Again, the same philosophy applies. Just draw them, and according to the gray coding order like this, and then put the corresponding values in there, and you can find terms like this. And if you have 6 variables, go to the same like this, and you will figure out, well, there's a term like this here. Right. So K-map is the universal tool that you can use for whatever number variables you have. All right. So hopefully this lecture today give you a very comprehensive idea about how to use K-map, and you know the power of K-map. And see, with K-map, we don't even need to memorize any of the theorem that you learned in for Boolean variables, right? Isn't that powerful? Isn't that powerful? Right. Okay, so a few things that I have to let you know. So first of all, we have assignment 1 due tonight, and it's on Zybook, and it's all the challenging questions up to 2.2. We have lab 2 due this Thursday, and watch the video, read the instruction before your session. There are links to on both course webpage and Island Lab section. Submit through Island Labs. There's no template. Just make sure that you cover all the questions. That's at the end of the lab instructions, and also attach your code as a single table. Our TA will handle that. And that's what they requested for, because I don't, being honest to you, usually the lab is handled by the TAs, and the lecturer doesn't even pay attention to that. And this time, because we are doing the hosting online, so I did spend some time revising, or say at least know what they are doing. So that's why we have a better connection between the lecture and the lab. But usually that's not the case. Right, and also the reading quiz, and usually the lab is completely handled by the TAs. And also for the reading quiz 4, we are going to have it up tonight, and it's due next Tuesday before the lecture. I don't want to see any emails saying that, well, it's I don't know, it's before the lecture, so I didn't submit it. I don't want to see that again. And assignment 2. It's also on Zybook, and it's all the challenging questions from 2.3 to 3.4. And after the lecture today, you should be able to tackle some of the questions between in chapter 2. Well, most of the questions in chapter 2, I would say, right? So in that case, don't wait until the last minute to start your assignment, and just submit it. Just do it on Zybook. It will be automatically recorded. And for lab 3, it's going to due on April 30th. And we know this time you are going to deal with a more complex case. So you are given 2 weeks to handle that. But I also don't want you to wait until the last minute to start your lab 3, because the week after you are going to have a midterm for this lecture. So I don't want you to ruin your life because you turn in your lab 3 late. And the reason why we try to pull up those lab sections as early as possible, because we are allowing you to, this would allow you to start earlier. Other than that, I will see you in the next lecture. Enjoy the rest of your day.